Okay, good evening class. Can you all hear me? Okay, let's kick it off. Today is a lab session. What I want you to do is I want you to go to this link over here, which I will send in the chat. Also, you need to let me know. So you'll have to flip between windows. Yeah, just cut and paste this in a new window. But if you need to communicate with me, you'll have to flip between windows. All right, is that clear? So let me just send you the link. Can you please cut and paste this in a new window. Keep the class window open, cut and paste this in a new window. Okay, if you can see my screen, can you go back to the class window and type on chat that you can see my screen? Just confirm. Okay, Mank, you've done that. Rashi, Divyangi, can you see? Okay, thanks Rashi. What about you, Divyangi? Visible? Okay, let me know when it's all ready. Okay, so here's the lab itself, and hopefully you can see the lab now. Rashi, Mank. Okay, that's the lab. Can you all see the lab now? Okay, very good. Let's kick it off. Here we go. So today's session is on work and energy, and I didn't give you all a quiz after the last class because work and energy is a little bit of a difficult idea. So it's important to understand it well before you can actually do questions on it. So I was hoping that we'll do this lab, and once we've done this, you'll hopefully understand the topic enough to be able to do the quiz a little bit better. Alright, so here we go. Here's what I'm going to do. So basically what we've got here is a skater. Yeah, this guy. And he can go up and down this ramp. Now a couple of things here, something called the potential energy reference. I'm going to click that, and that brings up this dotted line. So that's where the potential energy is measured from. Okay, I'm going to drag this right to the bottom. So really when the skater is at the bottom of this U, he's on the ground pretty much. Yeah, so his potential energy is 0. What I'm also going to do is I'm going to click on these energy bar graph over here, this button. Okay, and that brings up this energy chart over here. What I'd like to do is I'd like to align the lower end of this chart with the lower end with this potential energy reference line. Yeah, so we can measure what's happening to different energies. Okay, I'm also going to click on this grid box here. So that brings up a grid over here, and that tells us really we can measure the vertical height from the ground quite easily. Okay, everything clear up to this point? Okay, so here we go. So now what we are going to do is what I also want to do is I want to show you that I've opened up this friction box, okay, and I've set the coefficient of friction to 0. So our initial case, we are not going to be dealing with friction, okay, in the first experiment. Now what you see here is the speed of the experiment, and I'm going to set it at the slowest so that we can really watch what's happening quite closely. Okay, so it will proceed quite slowly, but that's fine. The idea is to learn what's going on. This is our play and pause button that allows us to stop the experiment or to just pause it, yeah, and see what's happening to the various parameters. Okay, so first thing we do is we take our skater and move him to the top, yeah, so this red dotted line is in between this purple point at the top, yeah, so that if let's count off how high he is above the ground vertically. So that's 1, 2, 3, 4, 5, 6, 7. Yeah, his vertical height above the ground is 7 units. Okay, and if you look at the potential energy here, yeah, this blue line represents potential energy. That's also going up to 7 units. Okay, so also note that at this point he's just waiting there, yeah, and so he's got no motion. We moved him and we kept him there. He's just waiting there. So he's at rest. At starting position is at rest. So he possesses no kinetic energy. So the kinetic energy bar graph, the green graph is 0. The potential energy is 7 units. Yeah, so his total energy at this point when he is in this starting position is comprised only of potential energy. Yes, and his total energy, which is potential plus kinetic, which is 0, is shown here, this yellow bar here, and that's also 7 units. Can you see all this? Everything clear up to this point? Okay, very good. So that's our starting position. Okay, now what we're going to do is I'm going to start the experiment and I'm going to try and pause it exactly when this skater reaches this bottommost point. So this red dot would need to be in the middle of this bottom purple circle, somewhere there, and that would indicate that he's at the lowest point. Okay, and so let's see what happens. All right, and we'll call this point A, we'll call this point B, and we'll call this point C. All right, so let's see what happens now. Here we go. I press play. As you can see, he starts to move down and starts to gain velocity. I'm going to try and stop him exactly at the bottom. Okay, little bit out, slightly out, but I've paused the experiment when he reaches the bottom. What's happened here? Can you see that his height above the ground is pretty much 0, and therefore his potential energy now has fallen from this value of 7 units to 0. Can you see this? Okay, but what I want you to also note is now his potential energy, his height above the ground is 0, so that's where we are measuring from, so his potential energy is 0. And we can see that that blue graph, which was at 7 units, has gone to 0. But the kinetic energy graph, which was 0 at point A over here, has gone from 0 to about 7 units. Okay, so if you look at it, what's happened? Okay, as he's slid down the slide, and remember there's no friction, his potential energy has gotten converted to kinetic energy. Yeah, so now so here it was all potential energy, no kinetic energy. Here it's all kinetic energy, no potential energy. And the total energy bar has not changed. Yes, it was 7 units in the beginning. It is still 7 units now. Okay, so really what's happened? What is this an illustration of? This is really an illustration of change in, of conservation of mechanical energy. Okay, now if you remember the last class, we did the work energy theorem. According to the work energy theorem, any work done on the body or any net work done on the body results in a change in kinetic energy, or the other way around, any kinetic energy increase of a body will require net work to be done on the body. That's what we studied in the last class. Okay, so what's happened here? At this point A, okay, his kinetic energy was 0. At this point B, he has significant kinetic energy, as we can see from this green graph. According to the work energy theorem, therefore, some work has to have been done on the skater for his kinetic energy to have increased. There is no other way that his kinetic energy could have increased according to the work energy theorem. So now, obviously that means when you say work has been done, it clearly means that there's some force acting and that force has moved some distance. What force is that? Very clearly, that force is the force of gravity. Okay? When he was at this point A, gravity acted down on him, downwards. Yes? As he slid down, so the vertical motion down, the gravity acts downwards. Then there is motion downwards as well. Yeah, so it's sideways, but there's a part of it that's downwards. So if you take that work done by gravitational force, that has brought about, that work is done on the skater, and therefore that has increased his kinetic energy. Now there are two ways to look at this. Clearly, yeah, if you can think about it, and this is similar to what we did in class as well. There are two ways to look at what's going on. One way is to look at it from a conservation of energy standpoint. Okay? The second way is to look at it from a work energy theorem standpoint, and we'll discuss all these ideas a little more in detail. Okay? So now, for the time being, let's look at it from the work energy standpoint. So clearly, in moving from point A to point B, gravitational force acted downwards. That gravitational force did work on the skater, and because it did work on the skater, the kinetic energy of the skater increased from point A to point B. Is this clear how this illustrates the work energy theorem? Okay, very good. So now we've paused him here, and now I'm going to unpause it and let the experiment continue. Remember, he's got some kinetic energy at this point. You can see that from the graph over here. So now if I continue to play, yeah, and which means that he continues along the way he was going from left to right, what's going to happen? Okay, I want you to think about it. So he has some kinetic energy here, which means he's going to move up. Now the question is, how far up is he going to move? Will he move to a height of 7 units from the ground? Will he move to a height of 5 units from the ground, which is somewhere over here? Will it be 3 units, which is somewhere over here? What will it be? What do you think? Where will he go to? Kirti, it should be in the chat. Scroll up in the chat, it should be there. Okay, rest of you, how high will he climb? 3 units, 5 units, something in the middle, 7 units, nothing at all? Any thoughts? Think about it. Okay, Divyangi says 7 units. Anybody else? So we'll call the units meters, yeah, just to keep it simple. Will he go 7 meters? Will he go 5, less than 7? Will he go more than 7? What will happen? Mayank, any thoughts? Okay, so let's see Divyangi whether you're right or not. Here we go. I'm going to play, and again I'll try and stop him at the highest point, and let's see what happens. Here we go. 1, 2, 3. And there he started moving up again, and keeps moving up, still going up, still going up, still going up, and about there. Oops. Alright, so roughly there. Okay, can you see that he's reached a height of 7 units? Can you see that? Yeah? And that should be natural, right? Because why was it 7 units? Let's think about this and let's verify that that is indeed the case. And so let me just move him back here, because that's where I should have paused him. Yeah? So what happened? What happened here? Look at his potential energy now. It's gone from 0 at point B. Let's call this point C. His potential energy was 0 at point B, but it's now become 7 units at point C. Yeah, at this point. But his kinetic energy has gone to 0. Can you see that? So what has basically happened is all his kinetic energy here has converted to potential energy. Now, why is this still 7 units? Think about it, yeah? Where did the kinetic energy here come from when he was at B? It came because he started at A, which was 7 units above the ground. It became all kinetic energy, and then it converted back only into potential energy. So it stands to reason, if no energy is lost, and because friction is 0, there is nothing lost as thermal energy, clearly all the energy remains mechanical. And therefore, if you started with 7 units of potential energy here, all of it got converted to kinetic. All of that kinetic got converted back to the same amount of potential energy, which again is equivalent to 7 units from the ground, 7 meters from the ground. Does this make sense? Why he went back exactly to 7 meters? Okay, so let's see if we can actually do the math on this. Here we go. So really potential energy, we'll call it U A equals UB, also UB equals UC. Okay, I'm sorry, my mistake. UA equals kinetic energy at B, and kinetic energy at B also equals potential energy at C. Potential energy and therefore I can write from this equation that potential energy at A must equal potential energy at C, which means that mgHA must be equal to mgHC, which means that this cancels, and which means that HA must equal HC. Do we agree with this? Sorry, I switched back to the whiteboard. I should have mentioned that. Okay, are we clear why the two heights are still 7 units? Okay, very good. Let's switch back to the experiment. Could you please switch back to the experiment? Actually, you should be able to see it on your screen. Either way, it doesn't matter, right? So, okay, never mind. All right. Let's also look at what happened in terms of the work energy theorem. The kinetic energy of the skater at point B was 7 units. The kinetic energy at point C is 0. Now, this obviously means that there is a change in kinetic energy, which means that some negative work has been done on the skater. That's the only way his kinetic energy can fall off according to the work energy theorem. So the question now is, okay, if there is some negative work being done, then clearly there's some force, okay, which is acting. So the question then arises, what is that force and why is it negative work? It should be clear that the force is again gravitation. There's nothing else acting on it, but this time gravitational force acts downward, but his motion is upwards, and therefore it's negative work being done on the skater. Can you see that? Because the displacement and the force act in opposite directions, negative work is being done on the skater. Because negative work is done on the skater, he lands up losing kinetic energy from point B to point C. Okay? Alright, so I'm going to start him off again, and I'm going to pause him somewhere in between. You know, we've looked at the extremes, we've looked at point A, we've looked at point B, we've looked at point C. Let's just start him off and stop him somewhere in the middle and see what's happening there. Here we go. 1, 2, 3. Starting to move. There, I've paused him again. Okay? What's happened? Clearly you've seen that his potential energy at point, let's call this point D. Okay? Clearly at this point D, the skater is above the ground. Yeah, he has some vertical height above the ground. So he has some potential energy. But clearly he was moving, so he also has some kinetic energy. And if we look at our energy chart, that's what it's telling us. He has some potential energy and some kinetic energy. And they are split in such a way that total energy remains the same. Total energy is conserved. Okay? The sum, when there is no friction, and we've set friction to 0, all energy is mechanical energy, and you can see that the total kinetic plus potential energy, which is the mechanical energy, remains constant, which is equal to 7 units. Can you see this? This is an illustration of the law of conservation of mechanical energy. Okay, so now I'm going to just press play and let him do his thing, whatever he does, and observe what he does. While you're observing what the skater does, also observe what's happening to the charts, energy charts. Okay, and see that it makes sense to you. This makes logical sense from both the conservation of mechanical energy standpoint as well as the work energy theorem standpoint. Okay, try and just rationalize it to yourself that you understand what's happening here. Here we go. 1, 2, 3. So as you can see, as he swings from one side to the other, there is no loss of energy in heat as heat. So mechanical energy is conserved, which means he goes from a height of 7 units, 7 meters from one side to a height of 7 meters on the other side, passing through the lowest point in the middle where all his energy is kinetic, which is about now. Yeah, and as he goes up, his kinetic energy drops, his potential energy increases, and this will keep happening till again he reaches the highest point. Okay, so now let's ask a question. Till how long will this continue under these circumstances? Yeah, how long will this continue? Will this go on for a minute, an hour, a day, forever? Okay, so Mayank says forever, and that makes sense, right? Because there is no energy loss. So he will keep doing this all day. yeah, because he's kind of stuck there. There's no way for him to lose his energy, if you will. Okay, so in that, that's a loose statement. Basically, none of his energy, mechanical energy, is getting converted to other forms of energy, and therefore he will keep doing this. Okay, that's really what will happen. But is that what happens in real life? We know that's not what happens in real life, right? In real life, what happens is the skater would slow down and come to a halt in general. Yeah. So now, what's the difference? Really, what is the difference between what we see? And yes, these just answered the question. And that's because in real life we come across friction. Okay, that's really what happens. Alright, so let's start again. Let me just pause. Here we go. Let's start again. What we are going to do this time is we will make, just give me one moment please. Yeah, what we are going to do is we will increase the friction slider to somewhere at the middle. Okay, somewhere near 50%. And as you can see, that's what I've done over here. Alright, again I drag the skater to the same starting point. Oops. Right, there we go. The same starting point, which is 7 units above the ground. Okay, that's the starting point. I've increased friction, as I've told you. Now let's again compare the energy charts, or look at the energy charts. As you can see, the energy is all potential at this stage. There is no kinetic energy because the skater hasn't started moving yet. So all his energy is potential energy. Also look at thermal energy. He hasn't started moving. Yes? Which means that since he hasn't moved, there can be no negative work done by friction. Remember, for friction to do for friction to do negative work, there has to be some motion, right? Remember, force times distance. So clearly some distance has to be covered before negative work done by friction will show up on him. He hasn't moved yet. If he hasn't moved, then clearly F times D is 0, because D is 0, and therefore nothing has been converted to thermal energy at this point. Everything at this stage is potential energy. Okay, also we note that the thermal energy is 0, kinetic energy is 0, potential energy stands at 7 units, and total energy stands at 7 units. Okay, before we get him to start. Now I'm going to start again. Okay, I'm going to press play. I'm going to let him come to B again. Okay, and this time we'll see how it changes from what we saw earlier. Here we go. I press play. There, I've stopped him at the bottom, or somewhere very close to the bottom. So what's happened now? What's the difference between this case? Look at the energy bars. Okay, look over here. And what's happening here? The skater's at ground level, at this potential energy reference level, which means his potential energy is 0. And we can see that's the case. Yes? He has clearly gained some speed. He was moving at speed when we paused the experiment, so he clearly had some velocity, which means he must have some kinetic energy. And you can see that here, the green bar, you can see a certain value to the green bar. But unlike the previous case, in the previous case when there was no friction, all the potential energy had gotten converted to kinetic energy, and the kinetic energy at point B had become 7 units. Now it's no longer 7 units, it's something less than 7 units. And that's because friction has done negative work. Because friction has done negative work, remember we said in class, what happens to the negative work done by friction? by frictional forces, it gets converted to thermal energy. Okay, and it's showing up as some thermal energy here, which is lost. Basically the man's skate his skate gets heated up, the ramp gets heated up, it gets lost to the environment. That's really what happens. Okay, but it's basically thermal energy, and this thermal energy is not mechanical energy. Can you see that mechanical energy is not conserved anymore, because the sum of potential plus kinetic energy at B is not equal to the potential energy at A. Yes? Do we agree? Okay, so that's important to understand, that mechanical energy is not conserved when frictional forces act. Okay, that's the point I wanted you to see. However, let's look at total energy, which includes thermal energy. So mechanical energy plus thermal energy, all three forms of energy, is still at 7 units. Can you see that? Even at B, which means that total energy is conserved. Yes? Okay, very good. So that's the important point. Now also, let's also try and link this up, what we see here, to the work energy theorem. Clearly gravitational force has continued to act, okay, while same as last case, absolutely the same as what was happened in the last experiment. In that experiment too, gravity acted downwards and the movement was downwards, so they're in the same direction, and therefore the work done by the gravitational force continues to be positive work, which contributes to an increase in kinetic energy. However, think about frictional force. Frictional force is acting up the ramp, okay, up the ramp, but the motion is down the ramp. So frictional force is doing negative work. That negative work leads to a reduction of kinetic energy, and therefore in the earlier case where you had only the positive work done due to gravitational force, that led to this full change in kinetic energy, that led to a 7 unit rise in kinetic energy. But this time you have that same amount of positive work done by gravitational force, but you also have negative work done by friction. So therefore the total increase in kinetic energy is something less than 7 units. So there you can think of it in two ways. There is because of positive work done by the gravitational force, this kinetic energy would have changed by 7 units. However, frictional force did some negative work, and therefore that reduced the kinetic energy to what we see here. And that reduction, that negative work, shows up as thermal energy. Is this clear? Okay, very good. So, but what's important to understand is that if you take all three forms, if you account for this, that there is some thermal energy also that has been created from mechanical energy, and you add up kinetic, potential and thermal energy, then the sum of this green bar and this orange bar is still equal to the total energy, which is still equal to 7 units. Okay, so clearly when friction acts, total energy including thermal energy, and remember thermal energy is equal to the negative work done by the frictional force. If you add up all the forms of energy, it is still conserved, and that's the law of conservation of energy. Okay, not just mechanical energy, but conservation of all energy. Okay, now I'm going to press play again. Okay, now I want you to tell me, think about how far will he rise up the ramp. Will it be 7 units? Will it be something else? Will it be more than 7 units? What will it be? What do you think it might be once I press play from this starting point B? Okay, I have 2 votes for less than 7 units. Okay, let's see if that's what happens. Here we go. I press play. 3, 2, 1. Here we go. I'm going to try and stop him at exactly the right time. Okay, there we go. That he's reached his highest point now, because as you can see, his kinetic energy is gone to 0, so he can't go any higher. He cannot go any higher. This is his highest point. So his kinetic energy has gone to 0. Some potential energy has come back, but thermal energy has increased even more. Okay, over here it was something like 2 units. Now it's something like 3.5 units. Okay, you can see that over here. Okay, so clearly, why is that? Because again, up the ramp, some more thermal energy has been created because of the negative work done by friction, and that's added to the thermal energy here. And the maximum possible potential energy he can have is the total energy that we started with minus what is lost to thermal energy, which is really corresponds to this height, about halfway, 3.5 units. Okay, let's call this point X. At this point again, the only mechanical energy that he possesses is potential, because he's stopped. There's no kinetic energy, but significant amounts of energy has been dissipated as heat energy. Okay, that's an important point. Okay, what's important to understand is there were 2 reasons why it was, starting from B. Okay, starting from B, why he rose to less than 7 units. So there were 2 reasons. The first is, from here to here there was some frictional force, and already he had started with less potential energy, less kinetic energy here than the 7 units, because some of it had been eaten up again by friction on this path. Okay, so the total energy available for conversion from kinetic to potential is a lot less in this case when you have friction, because significant amounts are getting used up in conversion to thermal energy. Significant amounts of mechanical energy are getting used up in conversion to thermal energy. Okay, just like the last experiment, if I press play now, what will happen? What do you think will happen? Will it go on forever? Will it stop? What might happen? Okay, I have 1 vote for stop. Anybody else? Okay, let's see what happens. Here we go. I press play, and as you can see, he starts to head. Look at what's happening to thermal energy. It goes on increasing. It never goes down, right? And so the mechanical energy becomes lesser and lesser as more and more of the energy is getting converted to thermal energy because of friction. There's very little mechanical energy left, which means that the heights that he can subsequently rise to, and his maximum velocity at the bottom, and therefore his maximum kinetic energy at the bottom, goes on reducing till at some point all of his initial energy has been converted into thermal energy, and therefore there is nothing left in terms of potential energy, absolutely nothing left, and that's the point he comes to a halt. And that's pretty close now, as you will see. Let me just increase the speed, otherwise we'll be here all day. And there we go, he's come to a halt. Yeah, there's nothing left, and the total thermal energy equals the total initial potential energy, and there's nowhere left for him to go. Yeah, because there is no energy left for conversion. Is this clear what's happened here in the second case? Okay, very good. What I'm going to do is I'd like to finish up the lab session with a couple. As you can see, it's quite a simple experiment, but there's a lot of conclusions to be drawn from a fairly simple experiment. What I'd like to do now is I'd like to basically take a few problems related to this. Can you guys please go back to the classroom? Let me just upload it. I need to put up a document here so that, give me one moment please. Okay, I'm just going to disconnect the screen share because there's no more lab left, so just go stay in the classroom, that's all. Just give it a minute and we'll try and attempt a couple of problems. If you've understood the ideas we've discussed, these problems should be quite simple. Okay, let me just start with the first problem while we wait for this to load. So let's say the skater, okay, has a mass of 50 kilograms. He starts from a vertical height at point A of 5 meters. I want you to figure out what is his velocity at point B, and we assume there's no friction in this case. Can you give it a shot? What is his velocity at point B? Just for your reference, that was the experiment. This point was A, this point was B, the lowermost, and this point was C. So what is the velocity at point B is what I'm asking you. If the mass is 50 kilograms and the vertical height of A above the ground, yeah, this is 5 meters. Anybody? Okay, I have a couple of responses. Okay, Kirti, that's right. Anyone else? Alright, here we go. It's fairly simple solution. At this point in time, all the energy is potential. At this point in time, all the energy is kinetic. There's no friction, which means that mechanical energy is conserved. So the total mechanical energy at A must equal mechanical energy at B. Okay, so mechanical energy at A equals the potential energy at A plus kinetic energy at A. Now he's not moving, right? He starts from this point. So kinetic energy at A is 0. So mechanical energy at A equals potential energy at A, which is equal to mgHA, which is equal to 50 kilograms times 10 meters per second times 5. Let's say his velocity here is Vb, as we said. Mechanical energy at point B is equal to potential energy at point B plus kinetic energy at point B. But this is at ground level, so therefore potential energy at B is 0. So mechanical energy at B is equal to kinetic energy at B, which is equal to 1 by 2 mVb squared. And this must equal 50 times 10 times 5. So which I'm going to write this as 1 by 2, just put in the numbers, times 50 times Vb squared must equal 50 times 10 times 5. That cancels, and I get Vb square as equal to 10 times 10, which means that Vb must equal 10 meters per second. Is this clear? Okay, second question. In going from point A to point B, from point A to point B, what is the work done on the skater? I want the answer in joules. What is the work done on the skater? And if you come to the conclusion that it's not possible to calculate this, then that's a fair answer also. But you have to let me know. Mank, if you need to answer a question like this, you can see in the... Do you know how to do private chat? Has one of the other faculty told you how to do private chat? Okay, very good. So answers in private chat, yeah? Okay, come on, shouldn't take that long. It's quite a simple question. Okay, you all are struggling. So what is the formula for work? Work done is equal to force times distance. Do you know what the frictional force is? Have you been told what the frictional force is? Oh, I'm sorry. I'm not even talking about friction here. Sorry, my mistake. My error. Okay, so it's really work done is equal to force times distance. The distance is in this direction along the ramp, right? Something like this. This is the displacement. Something like this. Yeah? In this direction. But the force acts downwards and the displacement is in this direction. So can you use the idea that work done equal to force into displacement when you don't know the force, neither do you know the distance? Can you use that idea? Can you use the formula directly? You can't, right? This is the formula. You don't know what is force, you don't know what is distance. How are you going to figure this out? So clearly that's not the approach. What you're going to have to use is the work kinetic energy theorem. What does it say? He started off at A, where his kinetic energy was 0. He reached a point B, where he had some kinetic energy, and we calculated the velocity. So KEA, his change in kinetic energy, is equal to the kinetic energy at B minus kinetic energy at A. And this was equal to 1 by 2 times 50 times 10 square. We just calculated that is velocity at B is 10. What is the kinetic energy at A at the highest point? Is he moving at that point A? Can you all hear me? Alright, sorry about that. Here we go. So, what were we saying? We were saying that, look, you don't know this distance, you don't know this force. Yeah, the force is acting down, the displacement is in this direction. Therefore, you don't really know how to calculate work done using this formula. So you can't use the direct formula. What you've got to use is the work energy theorem. Yes, do we agree with that? Alright, so how would we go about it? So let's figure out what is the kinetic energy at this point. Kinetic energy at this point, this is A, this is B. So change in kinetic energy is equal to kinetic energy at B minus kinetic energy at A. What's the kinetic energy at B? It's 1 by 2 mvb squared. Kinetic energy at A is 0, right? Because he hasn't started moving at this point. And so this is equal to 1 by 2 times 50, that's the mass, times 10 squared. Yeah, and that works out to exactly 2500 joules. This is the change in kinetic energy, and by the work energy theorem, this change in kinetic energy must equal the work done on the man, on the skater, and therefore work done on the skater is 2500 joules. Is this clear? Okay, very good. So if we understand that, let's try another problem or another case. Let's try and mathematically analyze another case. As we saw, the skater carries on from point B to point C, right? We've seen that. Hold on one moment. So this is A, this is B, this is C. And so we know that he carries on from B to C. Okay? What I want you to tell me is what is the total work done on the man in going from point A to point C? What's the total work done on the man? We just computed what is the work done on him when he goes from point A to point B. I want you to tell me what's the work done when he goes from point A to point C. Is it clear what I'm asking for? Okay, I have a couple of responses. Anybody else? I have one response from Kirti. Okay, that's the correct answer, Kirti. We'll just discuss why in a moment. Anybody else? Okay, What is the kinetic energy? Let's apply the kinetic energy theorem again. What is the kinetic energy at point A? Divyangi, Mayank, can you please, you need to participate. If you don't, then you're not taking away anything. What is the kinetic energy at C? You need to be trying to do these problems, okay? Don't wait for me to do them. Otherwise, you'll never learn application. What's the kinetic energy at C? When he goes from B all the way to the top and stops at C, what is the kinetic energy at C? Is he moving when he comes to point C? It's zero. He's not moving either at point A or at point B. His velocity is zero, which means his kinetic energy at both these points is zero. So between these points, delta Ke, the change in kinetic energy, is kinetic energy at C minus kinetic energy at A. This is zero, so his net change in kinetic energy is zero. According to the work energy theorem, therefore, the total amount of work done is equal to the change in kinetic energy, which, as we've just said, is zero, and therefore the work done on the man from point A to point C is also zero. Is this clear or is this not clear? Okay, last question. Let's say the skater starts again, okay, from point A, starts from point A again, which is again, as in the previous case, it's 5 meters above the ground. This time when he reaches point B, remember in the first case his velocity was 10 meters per second. This time when he reaches point B, his velocity is only 6 meters per second. That's because friction is acting. What I want you to calculate is how much energy is converted into frictional thermal energy. Okay, so same situation, same skater, mass 550 kilograms, starts 5 meters above the ground. But when he reaches B, instead of the previous case where it was 10 meters per second, and this time it's only 6 meters per second, I want to know what is the amount in joules of thermal energy that is created, and that which is also equal to the work done by the frictional force. How much is it in joules? Question. He starts at point A, which is 5 meters above the ground, exactly the same as the previous problem. In the previous problem, his velocity at B was this point B, lowest point was 10 meters per second. In this problem, I'm saying it's not 10 meters per second, it's 6 meters per second. It's lesser than it was in the previous case, exactly as we saw in the experiment, because frictional force is acting in this case. If frictional force is acting, it means some negative work is being done by the frictional force, which is getting converted to thermal energy. I'm asking you, how much energy is getting converted to thermal energy? Is this clear? Does this answer your question? Okay, Kirti, that's the correct answer. Rest of you need to give it a try. Yeah? You can't just be waiting. If you're just waiting for me to solve it, you'll never learn application. True learning is when you can apply what you've learned. Not just listening to the teacher or reading notes. That's not learning. Learning is when you can apply what you've learned. Okay, 30 seconds more. You really don't need that much time. It's really quite a simple problem. Okay, here we go. No, man, that's not right. Okay, so here we go. Here's what he did. This height is 5 meters above the ground. Let's talk about potential energy, which is U at point A, plus KE at point A, plus thermal energy at point A. This is the total energy, yeah, at point A. Similarly, you will have a potential energy at point B, you will have a kinetic energy at point B, and you will have thermal energy at point B. Do we first of all agree? Let's call this EA, or total energy at A. Let's call this total energy at B. First of all, do we or do we not agree that EA equals EB? Is this understood, or is there a problem with this? Okay. So what is, let's see you calculate the components. What is potential energy at A? Private chat, please. Simple. I'm asking you let's break it down. Private chat only. What is potential energy at A? Okay, Kirti. Divyangi, Mayank. Divyangi, without units an answer doesn't mean anything. Okay, fine. It's 2500 joules. What is kinetic energy at point A? Private chat only. Okay, man. Divyangi, let's ask a simple question. Is the man moving at all at point A? When he starts from point A, is he moving at all? If he is not moving, what will his kinetic energy be? Kirti, that's right. So simple. Why are you taking so long to answer such a simple question? Now, has any motion occurred since he started? He starts at A, he's still at A. Has any motion occurred at this point? No, it hasn't. And if no motion has occurred, has friction done any work at all? Remember, for friction to act, work done by friction must equal the frictional force times distance. If distance is 0, will friction have done any work at all? No, it won't. According to the work energy theorem, remember what we said, not work energy theorem, but remember what we said. Any work done by friction gets converted to thermal energy. If no work has been done by friction up to this point, what is the value of thermal energy at point A? Work done by friction is converted to thermal energy. That's what we discussed in class. We've just said that at point A, no work has been done by friction. Therefore, thermal energy must be how much? Exactly, Mayank. Divyangi, what must thermal energy be? You just said that work done by friction is 0. We also said that work done by friction becomes thermal energy. Therefore, the amount of thermal energy formed at A must be how much? Very simple question. How, Divyangi? Let's break it. Did you or did you not say that the work done by friction at point A is 0? Did you understand in class, or if you've read the notes, that work done by friction gets converted to thermal energy? We've just discussed that 3 or 4 times. Do you understand this idea? It becomes heat. So if no work has been done, how much energy has been converted to heat at point A? 0. So why are you giving me any other answer? So this is 0, this is 0, this, as you said, is 2500 joules. This is equal to EA. Let's take the components of EB. What is potential energy at point B? Exactly, Divyangi. Mayank, what is potential energy at point B? At point B, H equals 0, therefore mgh must also equal 0, yes or no? Okay, so this is 0. What is kinetic energy at point B? You've been told that the velocity at B is 6 meters per second. Divyangi, how do you get 0? Have you not been told that velocity at B is 6 meters per second? Didn't I tell you that the velocity in this case is 6 meters per second? Then if the velocity is 6 meters per second, how will kinetic energy be 0? What is the formula for kinetic energy? Yes, Mank, that's right. So why don't you calculate what is that value of kinetic energy, because that is the velocity at point B. Why are you saying 0? I'm not able to follow you. If you know the formula, you know what value of m is, you know what the value of v is, how do you say it's 0? Can you calculate that number that you will get if you plug the values into that formula? Okay, I really don't understand why this should take so long. Ke at B is, as you have written, 1 by 2 mv square. Can you please tell me what is the value of m? Divyangi, this question is addressed to you. What is the value of m? 50. What is the value of v? So times 6 times 6. This becomes 3. What is this calculation? If you multiply these three numbers, what do you get? 900 watt. What is the unit? What unit should I put here? What are we talking about? Just writing numbers is pointless. You have to have units. When you talk about physical quantities, you must have units. If you just write numbers, you get a big round zero. Joules. So why did this take so long? So now if you look at the same, let's look at the problem again. Total energy at A, which we said was equal to potential energy at A plus kinetic energy at A plus thermal energy at A, must equal potential energy at B plus kinetic energy at B plus thermal energy at B. We calculated this to be equal to 2500 joules. We calculated this to be 0. We calculated this to be 0. We calculated this to be 0. We calculated this to be 900 joules plus thermal energy at B. Now if you solve for thermal energy at B, what do you get in this equation? Exactly, Mank. And that's the amount, that's the converted to, that's the thermal energy. And therefore that's the negative work done by friction. Divyangi, I need you to solve this equation. Can you please solve this equation and tell me what is thermal energy of B? At B. You haven't given me an answer yet. 2500 equal to 900 plus thermal energy at B. What is thermal energy at B? Simple question. 1600 joules. That's the answer. Is this clear or is this not clear? I have no idea why this is taking so long. Divyangi, I'll tell you again, if you don't do quizzes, you don't practice questions, this is what happens. Okay, if you just coming and listening to classes is not going to do anything for you. You have to practice, you have to do the quizzes, you have to know what's happening, because one topic builds on the other. Okay, there are no simple, if you want to prepare for competitive exams in future, or even if you want to learn something, it's no use mugging up stuff. Mugging up stuff is not learning. Am I clear, Divyangi? If you don't do the quizzes, you will get nothing out of this program. I'm surprised that you're not able to solve really simple. I mean, this is really straightforward. We've done this 3 times already in just this class. Alright, that brings me to the end of this class. Hold on a minute, I'll give you the feedback link and then you're free to go unless there are any questions.